Welcome back, my name is Matthew, and in this video we're going to talk about the graphs of the sine and cosine functions. And if you're one of my students and you're using these printable notes and you want to pause right away, go ahead and write in the y coordinates that I've written in into these tables. I took the t values of 0, pi over 6, pi over 3, and so on, and I plugged them into the sine function and wrote down the corresponding y values in red. So if you need to pause, go ahead and do that now and write all of those in, please. And then I want to go down here and do some graphing. Now again, if you're one of my students, which I think most viewers are, and you're using these printable notes, you'll notice that this y-axis was pre-printed onto your notes for you. I have not yet modified or updated these notes and slid that over, so what I need you to do is to manually slide it over. I need that y-axis to be 3 squares to the left. And by doing that, you can see along the bottom there that it's allowed me to label every other square in increments of pi over 6. So we've counted 12 together before, and here it is again, but I've already reduced all of the fractions. 1 pi over 6, 2 pi over 6, 3 pi over 6, and so on, all the way out to 12 pi over 6. But like I said, I did reduce them already. So every other square, make sure that you write those in along the bottom, please. And then finally, on the vertical axis, I wrote in a -1 and a +1, down 4 squares and up 4 squares. And once you've got those labeled, then we're going to plot some points. We're going to take all of the points that we filled into the tables above this graph, and we're going to put those points onto this graph. Because we saw a little sort of a rough sketch of what this graph looks like in the previous video, but now let's get it a little more detailed. So the sine function does start at the origin. The most basic sine function does. So I'm going to get a point there at the new origin that we slid over to the left. And then I'm going to go 2 boxes to the right and 2 boxes up because we're plotting at pi over 6, 1/2. And then the next point that we're going to plot is at pi over 3, √3 over 2. And that, as I recall, is like 0.8 something. So it's getting up there. It's pretty close to the number 1, and this doesn't have to be perfect. So let's go there, and then 2 more boxes to the right and all the way up to the number 1. And now we're going to do that in reverse. So 2 boxes to the right and down a little bit to that √3 over 2 number. 2 boxes over and down to the 1/2 point. 2 boxes over and down to the horizontal axis. We just plotted the point pi, 0. And that was one of our quadrantal angles. The sine of pi is equal to 0. The sine of 1/2 you're seeing now again is equal to 1. Let's keep going. Now we're going to be going down below the x-axis here. So 2 boxes over, 2 boxes down to -1/2. 2 over and almost 2 down. 2 over and finally down to a y coordinate of -1. Another quadrantal angle, the sine of 3 pi over 2 is equal to -1. And then we'll start climbing our way back up. Over 2 up a little. Over 2 up to the -1/2. And over 2 and up to 0. The sine of 2 pi being the same as the sine of 0. Both of those are equal to 0. And then see what you can do about sketching in this curve. This is nice to actually have some points to bounce through. When I'm just freehanding these, sometimes it's tough to get the top of that hill to look good. And to get the bottom of that valley right there to look pretty nice, you got to come in at that bottom point almost from the side. Otherwise, your graph ends up looking like there's a sharp V down there. We don't want that. All right, there you go. That is a good looking sine graph. This is 1 period worth of the sine function. Remember that the sine function has a period of 2 pi. this graph goes from 0 to 2 pi, and the basic sine graph starts at the origin. Now that's in contrast to the graph of the cosine function. So if you need to pause and fill these in, please do that. And then let's go down here and modify this graph the same way that we did the previous one. It's all of those same x values horizontally along the bottom there. And I did put -1 and +1 on the vertical axis, up 4 and down 4 squares. Get all of those in there, and then we will plot some points. All right, now the cosine function at an x value of 0, or a theta value, or a t value, whatever it is, at 0 equals 1. So this graph, the basic graph of the cosine function, starts at its maximum output value of 1. And then we're going to come 2 boxes to the right and come down a little to that 0.8 something number. 2 boxes over and down to the 1/2. 2 boxes over and down to the x-axis. The cosine of pi over 2 is equal to 0. The cosine of 0 was equal to 1. And then we'll keep moving our way to the right. If I can get rid of that, there we go. All right, let's keep these points moving to the right 2 boxes, down 2 boxes to -1/2, right 2 boxes down almost 2, right 2 boxes down to the -1 for a y value, and the cosine of pi is equal to -1. Very easily identified there. Let's start working our way up, over 2 boxes, up a little, over 2 boxes, up to the -1/2, over 2, up to the x-axis, and the cosine of 3 pi over 2 is equal to 0. Got a y value of 0 there. And now we'll work our way back up to the maximum. Over 2, up 2, over 2, up almost 2, over 2, and up to the maximum y value of 1. The cosine of 2 pi is equal to the cosine of 0. Both of those are equal to 1. And that's no surprise because the cosine has a period of 2 pi. Sine, 2 pi. Cosine, 2 pi. Tangent has a period of pi. That's where we have to be careful. All right, see what you can do about sketching your curve. There's some satisfaction in actually getting this curve to pass through all of these points. The graph definitely ends up looking better if you can pull it off. Oh, I missed that one a little bit there. And right at the top of the hill. Nice. We're getting good at this. I like it. All right, so that's the graph of the cosine function. Now, the graph of the cosine function looks exactly like the graph of the sine function, except this graph is the sine function. If you slid the sine function to the left, a distance of pi over 2, you'd end up with this graph. So there are some similarities for sure between those two functions. Now transformations. We're talking about stretching, shrinking, shifting, reflecting, all things that you've done in an algebra class with parabolas. We're going to do them again here with these trig functions, at least sine and cosine in this lesson. And this is set up as sort of a little matching game. And Sophie's meowing at us. Are you coming in? Or are you just making noise? She's a little indecisive today. So this matching game, in the left-hand column, we've got some transformations. The first one has a multiple of k outside of our function. And that's going to cause either a vertical stretch or shrink. If the k value is greater than 1 or less than -1, it's going to cause a stretch. If the k value is between 0 and 1, or between -1 and 0, and I hesitate a little bit to mention the negatives, it's going to cause a vertical shrink. So those make sense, right? You put a big number out there and it's going to make the thing taller, up in the upward and downward directions. Now the next item on the left-hand column has the multiple of k inside the function, and those are the ones that have sort of a counterintuitive impact. The k value is in there by the x, which means it's going to modify horizontal stuff, and so we're talking about either a horizontal stretch or shrink, which is down here at the bottom. These are backwards, however. If you put a value like 1/2 in for k, that's when you're going to get a horizontal stretch and your graph will get wider. If your k value is something like a 2 or a 3 or even a 1.5, anything bigger than 1, you're actually going to get a horizontal shrink or compression of your graph. So be careful there. Let's go down to the fourth item in the left-hand column where we have a plus or minus k on the outside of the function, right? So the first two things that we addressed had the k value on the outside and then the k value on the inside. So I want to do them in the same order. K value on the outside in this statement right here is going to cause a vertical shift in the upward or downward directions. So modifications on the outside of the function impact y values. They either multiply the y values to make them larger, multiply the y values to make them smaller, in which case you get a compression from the top and from the bottom, or if you're adding or subtracting to the outside of the function, all of the y values will either shift up or down. Whereas if you add them to the inside, you're going to get a horizontal shift, which is a shift to the right or to the left, and those are also going to be counterintuitive. If you have f of x plus 3, even though it looks like a positive 3, you're going to end up shifting to the left in the negative horizontal direction, 3 units. So be careful. If it's happening on the inside of the function, the graphical result is probably going to be, I don't want to say the opposite, but let's say backwards from what you might think. And if there's a negation, the last elements in the left-hand column, they're happening. If you're negating your entire function, that's going to change the sign on all of your y values. So anything that was a positive y value becomes negative, all negative y values become positive, and you get a flip or reflection over the x-axis. Now, what we saw in that little matching game did not have a b value. You'll notice that all of these say, well, that's not true. All right, this looks like a b value. But otherwise, there's not a b value in front of this x right here. And we need to be aware of that. So this next part of the conversation is going to take into account the fact that we might have a multiplier on our x value in addition to having some adding or subtracting happening inside the function. So what do a, b, and c do to impact the graph? The a value is going to impact the amplitude, which is another word for either vertical stretch or shrink. And the amplitude specifically is a value that is equal to half the height of the graph. So if you look down at this example, the total height of the graph is here, right, like this, but half of that distance is what we're calling the amplitude. How do you figure out the new period of the function? Because if you have a horizontal stretch or shrink, you've modified the period. And that can be calculated by taking the period of the original function, which here it says 2 pi, and you take that value and divide it by b. This is the period of the original function. I'm going to point it out when we start working with the tangent function. I'm making that I'm highlighting this, the fact that it says 2 pi in the numerator, because when we're working with the tangent function and we start transforming that numerator is going to change to a pi. because the original period of the basic tangent function is pi. Sine and cosine, however, the period is 2 pi. We'll be dividing by b in either case, but just be careful that numerator is going to change when we get to tangent. And finally, the phase shift. Phase shift is how we refer to the horizontal shift. And that can be calculated by taking your c value and dividing it by the b value. So there's a depiction of all of those different scenarios. Oh, I want to back up and address one more thing. What these equations, graphs of y equals a sine bx minus c and so on, what they don't have in there is something that I think you should add in there at the end, which is a plus d, because that could appear also. We could end up with a vertical shift. It's not spoken about in the rest of these notes using a d value, but just be aware that it may pop up. So here's a chance for us to exercise what we've just learned about. Let's determine the period first. The period equals the original period divided by 2 pi. Since we're working with the sine function, the original period is, oh sorry, it's not divided by 2 pi, it's divided by b. I got a little carried away. The original period divided by b, there we go. The original period is 2 pi, and we'll be dividing by, in this case, a b value of 2. If it's helpful for you in your notes to come in here and write the a, the b, and the c, you're welcome to do that. And so the period of this function is equal to pi. There's that multiplier of 2 on the inside, which actually compresses the curve that we graphed earlier. And so if you sort of fix the point that was at the origin, let me use this hand, fix the point at the origin, you grab that curve, which looks kind of like a spring, and you just compress it, right? You make it half as wide, so the period's now going to be pi instead of 2 pi. And what about the amplitude? That's equal to the absolute value of our a value, which in this case is going to be the absolute value of 3, which is equal to positive 3. The fact that our a value is negative is going to cause a vertical reflection, or a reflection over the x-axis, and then sort of separately, the multiple of 3 is going to stretch our graph vertically. It's going to get higher and lower. So instead of it being a curve that lives between -1 and 1, it's going to be a curve that lives between -3 and 3. The swing will get larger. Amplitude got larger. And for a phase shift, PS for phase shift, that is equal to c divided by b. Now be careful here. What is the c value? You're looking at the equation and you're thinking, really? This is the question that he's going to put to us? All right, you're so smart. What's the c value? If you said pi over 2, you're incorrect. The c value is actually negative pi over 2. And that happens because this general format that we were looking at here says minus c. And if you want that to say plus pi over 2, then your c value better be negative pi over 2, so that it's really saying minus negative pi over 2. The double negative turns into a plus sign. So something to be wary of. So our c value is negative pi over 2. If you want to put a note into your notes here that explains what I was just saying about the fact that even though it looks like positive pi over 2, that this is indeed a negative pi over 2, write something into your notes. Phrase it in a way that you'll understand it when you read it later. All right, and so those are the 3 answers for this question. And then we're going to take that process and apply it to a graphing problem. We could do this one also. Well, this one's worth going through. It won't take too long. The period is equal to the original period divided by the b value. The original period of the cosine function is 2 pi. The b value here is 1/2. You can do keep change flip if you want, so that you're doing 2 pi times, let's just write it, 2 pi times 2 over 1. Some of you didn't have to write that out. Some of you, it's beneficial for you to write it out. And we get a period of 4 pi. So the multiple of 1/2 on the x value there inside the cosine function, even though it's a 1/2, it causes our function to get wider. It causes a horizontal stretch. All right, and what about the amplitude? Amplitude is equal to the absolute value of our a value. Maybe I should say AMP, so we don't have two a's there. And that's equal to the absolute value of 2 in this case, which is equal to 2. So no vertical reflection over the x-axis this time, but this graph is also going to get taller. It's going to leave that skinny little range of -1 to +1, and it is going to go up to +2 over -2. So a total height of 4, but an amplitude of 2. And tell me, what do you think about the phase shift? How do we calculate phase shift again? That was c divided by b, and we had to be careful with our c value. Have a look at this equation. What do you think the c value is? If you said 1, you're incorrect. I'm messing with you on this one, aren't I? Excuse me. I'm not messing with you in that well, let me just tell you what I mean. There is no c value. The c value is 0. Because there are not parentheses around that expression, the +1 is not inside the cosine function. It's outside the cosine function. So let's come back in here and label these components. There's an a value of 2, there's a b value of 1/2, and there's a d value of +1. So here the answer is 0 divided by 1/2, which equals 0. In other words, no phase shift. In other words, no horizontal shift. So put a box around that somehow, or write it in a different language, whatever's helpful to you. Note, however, that there is a vertical shift. D is equal to 1, therefore shift up 1. Nice. All right, so those can be a little bit tricky. There are some little details that you have to watch out for. And now we're going to be graphing. And is this function actually the same as that previous one? It is. 2 cosine 1/2 x plus 1. So we're going to steal some information from what we just did previously. Although it's on a separate page for you, so maybe we should write it in again. Period equals 2 pi divided by 1/2, which is equal to 4 pi. And the amplitude was equal to 2, and the phase shift was equal to 0, and the vertical shift was equal to 1. Great. So I have this question for you. She finally came in. I'm probably going to have to kick her out. She's been attacking me today, biting me and climbing up the back of the chair, and I think she's bored. Why she doesn't just play with her sister, I don't know. I want to show you how to use this table, and even if you're working on a problem where you don't have this table available, I think you can still use this thought process to make sure that you end up graphing things correctly. The original period, well, actually, let me do this. The original period of the cosine function is 2 pi, and the very first graph that we drew in the previous video and in this video went from 0 to 2 pi. So this table has 5 columns in it. And what we're going to do is take that period that goes from 0 to 2 pi and chop it up. The left end of it is at 0. The right-hand end of it is at 2 pi. The middle is at pi. Halfway to pi is pi over 2. Halfway between pi and 2 pi is 3 pi over 2. Those are the original x-coordinates of what I call the quarter points. 0 quarters of the way through the period, 1 quarter of the way through the period, 2 quarters, 3 quarters, and 4 quarters makes a whole, right? 4 quarters makes a whole, 4 quarters of the way through the period. Now, well, we might as well fill them in while we're here. The y values, the original y values at those 5 quarter points, the cosine of 0 we learned is equal to 1. The cosine of pi over 2, a quarter of the way through the period. Remember that the cosine function starts at its maximum and then it dives down to the x-axis where it hits a y value of 0, and then it goes all the way down to its minimum, and then it climbs back up to the x-axis, and then it goes back to the top of the hill at its maximum y value of 1. So those are the values that we're starting with. And for this particular function, the period changes from 2 pi to 4 pi. How do you change a 2 pi into a 4 pi? Maybe we switch colors here. Multiply by 2. I'm going to multiply all of my original x-coordinates by 2. 0 times 2 is still 0. Pi over 2 times 2 is pi. This becomes 2 pi. This becomes 3 pi. This becomes 4 pi. Now, I wrote those in, and I didn't say this in advance, so it's fortunate for me that it just worked out this way. There was no phase shift. If there had been a phase shift, then we would have done that multiplication, and then we would have added or subtracted whatever was necessary in order to apply the phase shift. We're going to do another problem after this. I forget if it has a phase shift in it, but I'll mention it again at that point. Now let's look at our y values. And you should keep adding more and more notes into this, whatever's going to help it make sense for you. The period has to do with x values. The phase shift has to do with x values. The amplitude has to do with y values, as does a vertical shift. So with regard to the y values, we do have 2 modifications. The amplitude being 2 tells me that we're going to multiply all of those y values by 2, and then we're going to take our y values and add 1 to them. So let's do that. Our original y value is 1. So it's double it and add 1. That makes this a 3. Double this and add 1. Double the 0 and add 1, we get 1. Double the negative 1, it becomes negative 2. Add 1, and it comes back to negative 1. Double it and add 1. Double it and add 1. So you're still seeing a pattern. We're starting out even higher at a y value of 3. We're coming down to a 1, and then down to the minimum of negative 1, and then we're climbing back up through those same y values. So there is going to still be this kind of flow that matches the original shape of the cosine function. It's just going to be stretched a couple of different directions and shifted up a little bit. Okay, so let's write down in this last row the actual coordinates that we're going to be plotting. We'll plot 0, 3. It's even easier to see because I did it in 2 colors, but if you're taking a test or you're doing a quiz or a homework assignment, all you have is a pencil or a pen, only 1 color. Helpful to just go ahead and write down these coordinates to make sure that you plot the correct points. All right, and then I'm excited to plot some points. I want to see what this thing looks like. I have not modified this graph yet, so I'm going to pause real quick and then snap back to an already labeled graph. If you want to flip back, you can look and see what your graph looked like, or just wait a second and it'll be done. Actually, I haven't done anything yet because this graph's a little bit different. So hopefully you haven't gone and done modeled after the previous graphs. Notice the largest y value on this graph goes up to 3, and the lowest goes down to -1. So I don't think we want to, especially in the vertical direction, we don't want to be using those same vertical labelings on the y-axis. So let's actually look at this together. We want to be available to go all the way up to a y value of 3. So I think maybe I'll just go ahead and let's just go up 3 boxes, and that'll take us to, no, because we want it to look like a stretch. Let's go all the way up to the top. Let's have, hold still. Let's have this be 3, and this can be 2, and this can be 1. So 2 boxes vertically will have a value of 1, and then we do need to go down to -1, so that'll be here. And then horizontally, we need to be able to go from 0 to 4 pi. So let's leave that existing vertical axis where it is. If you already moved it, don't worry, just leave it there, scribble it out, erase it, whatever. We can use this original vertical axis. And then what we're going to do is we're going to use 4 boxes horizontally in order to, four horizontal boxes will equate to 1 pi. So under the axis, I'm going to label it with a 0, then I'm going to go to the right 4 boxes to pi, 4 boxes to 2 pi, 4 boxes to 3 pi, and 4 boxes to 4 pi. And then we can plot some points. I think that's all we're going to need. Get those values available again. Great. So 0, 3, I'm using the original vertical axis. 0, 3 is all the way at the top of that axis. It's right, did I point? There it is, yep. And then pi, 1, 2 pi -1, 3 pi 1, and 4 pi 3. There it is. And you can draw your curve through there if you wish. I recommend it. A little bit different than our previous one in terms of the scale of it. Don't have as many points to pass through. That should have actually gotten up to the very top of there. There we go. And that's your graph. Nice work. Oh, I remember this one now. Yeah, so we have the chance to do another one of these, and I don't really like this one. I don't like it because it's so strange because it has pies in it, and that's going to happen pretty infrequently. Maybe in the real world it happens, but in academia, this is in here just for variety's sake, but it's going to happen so infrequently. I'd like to modify this one. We just worked with a cosine function. Let's work with this as a sine function. We will include the negative leading coefficient there. We'll keep it as a sine function. And then let's have it be, the 2x is still good. And then let's add, oh, I don't know. Do we want to add 4? So it would be 2, maybe 4 pi? No, that's too much. We could just add pi. Let's add pi over, let's add pi over 3. Let's subtract pi over 3. And then we don't need that. As a matter of fact, let's just make it go away. All right, we need our 3 different aspects of this. We can actually address all 4 of them. One of them is going to be a 0. Let's talk about the period first, if my pen will write. I was just checking to make sure that I'm recording. The period is equal to the original period divided by 2 pi. The original period of it's not divided by 2 pi. Why do I keep doing that? It's divided by b. The original period is 2 pi. We're going to divide it by a b value of 2. And that is equal to pi. So the period is getting compressed. Oh, it was a 2 in the previous problem. I was thinking it was a 1/2. No, it was a 1/2 because we went to 4 pi. Perfect. So we have a compression this time, a horizontal shrink. The amplitude is equal to the absolute value of our a value, which here is the absolute value of -3, which is equal to +3. So we're going to get a vertical stretch, and we're going to get a reflection over the x-axis because of the negative. And the phase shift is equal to c divided by b. All right, redeem yourself. What's the c value in this equation that I've created for us? The c value is positive pi over 3. We're subtracting a what? A positive pi over 3. So let's put that in here, pi over 3. We're dividing that by our b value of 2, which makes this equal to pi over 6. And what about a vertical shift? Am I messing with you on this one at all? No, there is none. No vertical shift, no d value at the end on the outside of those parentheses. We're not adding or subtracting anything. Okay, for the sine function, let's write in our original x values. Those are the same as they were for the cosine function. We've got 0, pi over 2, pi, 3 pi over 2, and 2 pi. The original y values are different because the sine function starts out at the origin. So we've got an original y value of 0. It'll go up to its maximum of 1, come back down to 0, dive down to its minimum of -1, and then come back to 0. Great. Now, the period is pi. How do you change a 2 pi into a 1 pi? You cut it in half. So we're going to be multiplying all of our x values by 1/2. The period impacts x values. The amplitude impacts y values. What are we doing to our y values? We're actually going to be multiplying our y values by -3. It's true that the amplitude is 3, but in order to induce the vertical flip over the x-axis, all we have to do is multiply our y values by -3. And then our phase shift, which impacts x values, is pi over 6, positive pi over 6. So we're going to be adding pi over 6 to all of our y values, or x values, sorry. So that'll be a little bit tricky. We'll have to make some quick common denominators. And all right, so let's work on the x values first. So we're doing times 1/2 plus pi over 6. Times 1/2 is still 0, plus pi over 6 makes pi over 6. Times 1/2 makes pi over 4, and then we have to add pi over 6. Let's just do some arithmetic off to the side. Pi over 2 plus pi over 6. Oh, we can change the pi over 2 into a 3 pi over 6. That's nice. And then we'll just cross out the pi over 2. Forget that. All right, so we've got 3 pi over 6 plus 1 pi over 6 makes 4 pi over 6. I'm just going to write it in first as 4 pi over 6. We'll come back for it in a minute. What's the distance? And this time it is a physical distance because we're graphing it. What's the distance from pi over 6 to 4 pi over 6? The difference between those is 3 pi over 6. So if going from here to here is 3 pi over 6, guess what it's going to be to get here? Another 3 pi over 6. Now, I don't want to detract from the bliss that you would get from taking pi, multiplying it by 1/2 to get pi over 2, and then adding pi over 6 to it. Why does that sound familiar? Didn't we just do that? All right, now I'm getting nervous that I misspoke. I'm backing up. Just hold the phone. Oh, it won't do individually. Darn it. All right, I think I made a mistake. And that happens, but I'm glad I caught it now instead of later. Let's take the pi over 2, multiply it by 1/2, and add pi over 6. Pi over 2 times 1/2 plus pi over 6. That's what I didn't do. I never multiplied it by 1/2. So it's pi over 4. I think I said that out loud, but then I didn't write it down, plus pi over 6. All right, so now we need a common denominator, which is going to be 12. So that's 3 pi over 12 plus 2 pi over 12 makes 5 pi over 12 So that's our next x-coordinate, 5 pi over 12. Now pi over 6, right, here's where I'm going to be fancy again. Pi over 6 is 2, that pen's too fat, 2 pi over 12. What's the distance from 2 pi over 12 to 5 pi over 12? The answer is 3 pi over 12. So it's going to be the same as we move over to here. So I'm going to take 5 pi over 12 and add 3 pi over 12 to it to get 8 pi over 12. And then I'm going to do that again. 8 pi over 12 plus 3 pi over 12 makes 11 pi over 12. And then again, adding another 3 gives me 14 pi over 12. Now this is what I get for making this problem up on the fly, because graphing pi's over 12 is going to take a little bit of effort, but we're smart, we can do it. If I were typing these numbers into a table or somehow selecting them as multiple choice options, I'd want to reduce them. I'd want to use the pi over 6, not the 2 pi over 12. The 5 pi over 12 is fine. The 8 pi over 12 I would reduce by a factor of 4. Let's take it down to 2 pi over 3. That's nice. We'll be able to plot that as an x-coordinate pretty easily. 11 pi over 12 kind of stinks. So we like this one. We like this one. We're bummed that we have to graph this one, but we're stuck with it. And then 14 pi over 12 reduces by a factor of 2. We get 7 pi over 6. I like that. I'm more familiar with graphing that. All right, so we'll be dealing with those in a moment. Let's check out what I did to us as far as our y values is concerned. All we have to do to our y values is multiply by -3. That's great. 0 times -3 is still 0. -3, 0. +3, 0. Just multiplying by -3, and then I'm going to write down the points that I'm going to plot. 0 pi over 6. Nope. You're supposed to be writing these down carefully so that they help you, not become your undoing. The x-coordinate was pi over 6. The y value was 0. There we go. Then 5 pi over 12, comma -3, pi comma 0, 11 pi over 12, stoked about that, comma 3, and finally 7 pi over 6, comma 0. All right, this is going to be fun. How many squares do we have? 2, 4, 6, 8, 10, 12. Nice. 11 pi over 12. Oh, 12's not good enough. We need 14 at the very least. I think we should move our vertical axis again. Let's do that. Let's move it all the way over to here. Let's take it all the way to where we have been. 1 square away from the left. We don't need that pre-printed y-axis. Forget about it. And for y values, we need to be able to go from -3 to +3. So let's tighten this up a little bit. Let's just have this be 3 and -3, so that each square vertically is equal to 1. 2, 1, 0, -1, -2. And horizontally, I think that we should have each square be worth a pi over 12. So let's come down to the bottom here. Pi over 12. And then let's be strategic about this. I only want to write out so many pi's over 12. Pi over 6 was 2 pi over 12, remember? So we definitely need to write down a 2 pi over 12. And then remember also that the difference from 2 pi over 12, where am I? I'm up here now. The difference, or the distance from 2 pi over 12 to 5 pi over 12 was 3 pi over 12. So we'll go every 3 squares and label them. That's 1 pi over 12. There's 2 pi over 12. Move to the right 3 boxes for 5 pi over 12. 3 boxes to the right was 8 pi over 12, which we reduced to 2 pi over 3. And then another 1, 2, 3 boxes to the right. Oh boy. Lost it again. Let me write it in real quick. 11 pi over 12. And then we'll unplug and replug. Sorry about that. 3, 2, 1. Oh, there we go. Sky got scared for a second. And then we need to add another 3 to get to 14 pi over 12, which we said was 7 pi over 6. All right, let's plot some points. We've got pi over 6 comma 0, which is the same thing as 2 pi over 12 comma 0. And then 5 pi over 12 negative 3. Pi 0. Oh, pi. Where's pi? 5 pi over 12 plus 3 made 8 pi over 12. Why did I write down pi 0? Oh, just because my eye was playing tricks on me. I should have written 8 pi over 12 or 2 pi over 3 right there. So this needs to be a 2 pi over 3. I think I'm getting tired. I must need a break. I wrote the 2 pi over 3 down here. All right, that was 2 pi over 3 comma 0 because we're swinging back up to the horizontal axis. At 11 pi over 12, we need to go up to the max. At 3 and at 7 pi over 6, we're coming back down to 0. And then we can draw our curve through there. Now this is interesting because it's an upside down sine curve. So we're coming out of this leftmost point on our way down to our minimum already. Then we can start heading back up to our maximum and then back down to that sort of a midpoint. All right, that was a bit of a wild ride. Sorry, there were a couple of hiccups there, but that happens. Just have to keep an eye on your own work and hope that it speaks to you if something has gone wrong or if your eye just grabbed the wrong number out of a table. I am human. It does happen. And let's see what's on this last page here. Find an equation that describes the graph. I made 2 mistakes in the last problem, which leads me to believe that I'm tired enough that this I could probably make a disaster out of this. Let's see what I can do. You've got options because the sine and cosine graphs are so similar. We could think of this as a horizontally shifted cosine graph. We could think of it as a vertically reflected sine graph. And I think that's what I'm going to do for this problem. If you're one of my students and you want to do the cosine version of this in class, if we have time, make that request the next time I see you. Otherwise, let's see what we can do. We're going to try to use sine. And this is definitely has an amplitude of 2. It's also been vertically reflected. And what those two things mean when you put them together, it means that our A value is going to be -2. Now let's look at the graph a little bit more closely. And if we look at one period worth of the graph, and we could look at that period by examining it here, I think you can tell that that is a part of the graph that could then be copy and pasted to the left and to the right. I kind of grabbed the middle portion of it. And what's the width or the period of the function of the graph does it appear to be? We went from 0 to pi just there. So the period appears to be, and if you want to put some notes on your graph, maybe you could say let's go from here to here. Period looks like it's equal to pi. Now, if the period is pi, and that's found by taking the original period and dividing it by 2. And the original period of the sine function is 2 pi, and we're dividing that by, oh, sorry, I haven't gotten this right once. It's the original period divided by b. And the original period of the sine function is 2 pi. We're dividing it by, we don't know what our b value is, but we know that the period's going to turn out to be 2. So the period is going to turn out to be, see why I was hesitant to do this? Because the period of this function, the one at the top of the screen, is pi. We determined. There it is. And in fact, if you're using multiple colors, maybe you should write this pi in red so that it matches with that pi that's in red up there. Okay, we calculate the period by taking the original period, which is 2 pi, and dividing it by the b value, which is unknown. But we know that 2 pi divided by b, we want it to equal pi because the period of the graph that we're working with is pi. So what must the b value be? Well, if we solve this little equation right here, that's an arrow, by the way, we find that b must be equal to 2, so that the 2's cancel and we're left with just a pi. There is no phase shift based on the way that we're choosing to examine this, so we don't have to worry about that. I think we can go and just write down our final function. Call it your answer, call it your solution, the final function. We could use function notation. We could just say y equals -2 as our a value times the sine of our b value, which is also 2, times x, or while we're doing y's, let's do x's. Perfect. So that graph was of a function that had been vertically reflected over the x-axis, horizontally shrunk, and vertically stretched. There's a trio of transformations. That came out nicely. Involved in creating the equation for that graph. Nice. All right, I'm going to go see if I can get my head screwed on straight again, and I look forward to seeing you next time. Thanks for joining me.